All right, good afternoon. I'm Cameron Schmeits. My colleague Nabil is not here, but he's a very valuable member of our research team. So my topic is visualization for decision support on North Texas projects. So I work for UT Austin, the Center for Transportation Research. I support the Texas Department of Transportation with visualizations during mostly the construction phase. So, and the projects I'm talking about now are a special type of project called public-private partnerships, and I'll talk about those in a little bit. So not just me and Nabil on this, we have several other people that support us from the TxDOT side, and also the Center for Transportation Research side, such as graduate students or professional staff. So I'd like to talk about public-private partnerships real quick because they provide us a unique type of delivery where visualization can be very valuable. Also, the two case studies are on there. And then just go over the benefits of how visualization helped those case studies and talk about our conclusions. So public-private partnerships, not sure if y'all are aware, but just go over it quickly. What they are, at least for my topic is they are very conducive to delivering very large, very complex projects with a rapid schedule and also very innovative design solutions. So according to TxDOT, they enable private development by sharing the risks and responsibilities of design and construction. So that'd be like design build. And then in some cases, they also finance the transportation system as well. And on these, they do that. They have provided their own funds for the project. So they also open the door to accelerated financing, design, construction, operations, and maintenance. So that's where we get the expedited delivery piece. They help us develop regional projects of much larger undertaking. So large projects, and then by their nature, PPPs reward innovative thinking, so innovative designs. So public-private partnerships, from the owner's perspective, they have transferred some risk, some responsibilities to the private sector, but they are still a big player in this, and they are the public's representative for the project. So they are very concerned about quality. They want to make sure that the bridge does not fall down. They want to ensure that they are not reducing any scope, whether that be, I know on the LBJ Express project, I think they kind of tried to sneak in, well maybe they'll say they accidentally had a 4-foot shoulder instead of a 10-foot shoulder. They want to make sure that while the project's going on, that they're limiting traffic impacts for the public, and the project's meeting the future needs, that it's interfacing with adjacent projects, whether they be existing infrastructure or under construction. And then more and more, your roads are getting more beautiful if you're driving through them, and that's for the architectural requirements. So what I'm saying here is basically is that the owners have quite a bit of responsibility. And so, but in the TxDOT's case, they don't really have a lot of resources that are on these projects. On the LBJ Express project, there was 5 engineers, and on the NT project, there was 4 full-time engineers in the office. Now they had backup staff, but really the people that know about the project are on the project every day, that are making decisions for the project. They're running from meeting to meeting to meeting. So visualization is helpful for them because you can see it, it's quick, you can make a decision. And I'll show you how we did that. So LBJ Express is in Dallas. You can see there in purple, and the 4th project is NTE. It's in blue, running from downtown. So let's talk about LBJ Express. Basically, very large project, very quick delivery. $2.6 billion delivered in less than 5 years. I believe they were at one point doing $60 million in construction a month. So $2 million a day they were spending. It's 17 miles, and what they're doing is they're adding capacity via managed toll lanes. And then they're going to rebuild the highway lanes and then provide a continuous frontage road system. So here's some cross sections. There's what it looked like before. Here's what it looks like now. Those roads overlap. Okay, that's interesting. And that's where we were helpful, is we were looking at the managed toll lane system and the geometry and the setup of that, and what is, it's not really a tunnel. It's not really an open depressed section. It's got these really long bridges, basically, that support that overlap. So you have these bent caps that are like 7.5 feet deep every 100 feet for 3 miles. It is awesome. So that's where we were helpful. Is we were the project manager came to us and said, hey, you know, we have these bents over there. Are we going to be able to see the signage? And then also they were worried about, hey, what do these bents do if you have the sun right in your eyes? You know, am I going to get like this flashing effect? They were actually really concerned about like seizures from that while you're driving. And so that's where visualization really helped them. So I'm going to go ahead and show you one of the videos that we did for them to look at that. So we were brought on, we were there on the owner team for the whole project. We created a 3D model and then kind of basically, you know, used it for several different applications. So in this case, what we were able to do, okay, left is actual image and right is the rendered image. So you can see kind of the comparison of how good do we get. So we took our 3D model of the whole project, and then for the signage, we were able to take the plans and just model those as well and drive on the highway. You know, we set up a rendered animation where we're driving at 70 miles an hour in the middle lane, you know, like 3.5 feet, basically what you would see if you were driving a sedan down in those lanes before they were constructed. And, you know, looking at, can you see the signage? You know, the horizontal, how does the horizontal vertical geometry really affect that from the driver's perspective? And then once they saw this, they were like, oh yeah, remember we had that concern of that flashing effect, you know, is this how it's really gonna look? So we took this and so there's one of the signs. We didn't put the faces on them because we delivered this in about 2 weeks. So they said, you know, is that the real lighting? So we played with the lighting. We kind of looked at it, looked at some sections that were actually built. And so we were able to show them exactly, you know, within a 30-minute meeting, hey, here's what it's going to look like. Here's kind of what the shadows are going to look like. We modeled eastbound, westbound, all 6 miles, all of the signs. We looked at various types of day, you know, basically, you know, what happens in, you know, this is an east-west road. So basically what happens when the sun's like right in your eyes at 6 a.m. or what happens like, you know, right when you're driving the other way at 6 p.m. or, you know, does it change? How does it change throughout the year? So we did lots of videos and analysis for them. So what did we get? Basically what we said was, there's no problem with signage. Awesome. With sunlight, as you could probably see, there was not that flashing effect. So that was a positive. You really just weren't traveling fast enough. I guess maybe if you're traveling at hyperspeed in the new Tesla that Alex likes, you could have it. But, you know, we were wondering, you know, maybe those shadows are kind of annoying, kind of weird. You're paying a bunch of money to drive down there. So they sent it over to the developer, and the developer said, you know, we don't think it's a big deal. So what did the model do? First of all, it integrated numerous highway components. We had the correct horizontal vertical geometry as on the plans. We had the correct sign faces, the correct stationing. It was what it was really going to look like. It was all modeled to scale. And then also we added in these other dimensions, such as, you know, driving speed. We were driving at 70 miles an hour, and then also a light source to analyze. We didn't find any issues, but if we did, we would definitely have time to address them. And then for TxDOT's benefit, it was very concise and easily understood. In a 30-minute meeting, we, you know, took care of their concerns. Next project is NTE35W, not as large as WJ Express, but again, they're delivering $30–40 million a month at the height of construction. So they were doing this in less than 4 years. It's currently under construction. And again, what they're doing is they're adding capacity by basically taking the existing lanes, move them out, slip managed lanes in there. So it's almost like I have to model 2 highway systems, which is awesome. Challenges on here. They decided, you know what, we're just going to plan for the project that we want. And then they said, oh, we don't have enough money. So what they tried to do is they took a reduced scope called the interim version. That in some areas is easily compatible with the ultimate version that they want to build maybe 20–30 years when they get more money. And when I say compatibility, what I'm talking about is that there's no major demolition. So they're not going to have to demolish a bridge when they go from interim to ultimate, or they're not going to have to demolish drainage. What they can do is they add on to a bridge, or they add in some pavement, or they build a new rail. However, that was an issue near a certain interchange. There was an interchange with 121, as you can see, it's running right along here. And so this is what they're going to build in the interim. Basically, all they have money for is just to kind of add in these managed lanes via bridge. Here's what they want to build. That is actually the same project. You can see here's the road. These roads match up right here. So in this area, they said, this is $500 million. We don't have enough money. So you don't have to be compatible coming into this interchange or going out of it, really. So there's areas, the interchange itself, and then the areas kind of transitioning into that interchange. We're not able to be compatible, and from a cost perspective, it just didn't work out. But they got some additional money. Woohoo, yay, we love money. So they got about $70 million, and they said, okay, what do we want to do with this? And their idea was to provide more access to that managed lane system, that kind of highway in the middle. And so 2 areas they did that. The first one is the I30 Connector. This was actually not in the Ultimate, but it was so smart. I don't know why it wasn't a part of the Ultimate. I just don't think it was part of the study. What it did was it provided a direct connection from I30, and I30 runs right through the middle of downtown, and 35 does as well. Downtown's kind of in this corner right here. So what they did is they said, okay, how can we, and this is one of those areas where they, there's not, as you can see from the colors, there's not much construction that they were going to do in this area. So they said, okay, with this, how can we squeeze this kind of new ramp in? That's where that innovative design comes in, with the private sector. So I'm just going to show you a video of it because this is a visualization conference, and that's probably best. So again, what they're going to do is they're going to take the existing direct connector, peel off of that, and then kind of hop into that managed lane system in the middle. And this is just kind of nice to provide people context. So downtown Fort Worth right there. So you can build anything with money, right? But here it's like, okay, this is under construction. We have a bridge that we have already built columns in. How can we squeeze it in? So I30 connector, like I said, kind of peels off that existing direct connector, 2 giant straddle bends to hop over the existing highway, and now we're in the toll section. So this kind of changed the way, that area kind of changed the way that normal traffic enters the managed lane system. So that was kind of the beginning of it. So what they were able to do before this is that this is the highway, that's all that's there. And then this is the entrance into that managed lane system, which is that highway within a highway that is tolled. And so less people are on it, so you can drive faster. So whenever they added this new direct connector, and that changed the way that traffic came in, now they have to merge. So a couple of things, managed lane system design speed is 70 miles an hour. This roadway is 60 miles an hour, and this direct connector is 40. So in this section, how do you design that? Do you design it for 40, 60, 70? What do you use for acceleration and merging distance? And we said, okay, well, let's look at it from a driver's perspective. So took that same model and got a different view of it. So again, what we're doing is we're simulating a driver. We're driving 60 miles an hour, basically like you're in a car. We've got everything modeled for you. So direct connector's on the right, and it hops over. That bridge is existing to remain. You got this retaining wall, you've got this barrier. Will I be able to, find a gap from all these cars? And while we're traveling at 60 miles an hour, during You know, the peak, this is a city. You might not be able, when you're in the free lanes, you might not be traveling at 60 miles an hour. You might be traveling at 0. And then these people are coming down, you know, they've been driving for about a mile. They're going like 120 miles an hour because they've been sitting on that ramp for days, it seems like. So we showed TxDOT and we showed the developer that. And so what happened? Well, what it was is that we said, we've looked at this several times, but, you know, via the schematic, which I showed you earlier. But what we didn't see is we didn't see that the only thing that stopped us from moving this merge was a column. That column's right there. So we have plenty of room to kind of move that gore and create more space. We looked at that drawing several times, but 3D just gave us a different perspective. So what we did was we moved it. So you can see the gore is, you know, right there. This is the new gore. You see it's significantly further to the north of this bridge than it was before. So, you know, just looking at it in 3D, who knew? Different perspective, more information. Another addition that we had, this is in that same 121 interchange, you know, where it's going from nothing to craziness when you get to the ultimate. We had some more money, so we decided to add in this connector. And so 121 is a highway, but then basically it kind of terminates into city streets that are in downtown. And so they wanted to provide people access from downtown to the managed lanes so they could get home. In the DFW area, we have urban sprawl, which Lele talked about. So people drive, I drive 29 miles to work, and that's about average. So having access to those managed lanes is very important for those people. So like I talked about earlier, we have architectural requirements that are becoming more and more a part of our highway. And so since we were coming into downtown Fort Worth, the city of Fort Worth wanted to have an architectural element because the existing highway that it's tying into has that architectural element as well. And that you can see in the orange, that's kind of highlighting the existing rail on 121. And they had this nice, beautiful rail, nice, beautiful lights, and you can see downtown in the background, how close it is. So the city of Fort Worth wanted to add that same rail to the connector. And so we said, oh, we can't really do that. The design speed doesn't work. It can't work for high speeds because there's not enough structural. But we can do it on this little portion in yellow. And so talking about stories, so public and private partnerships, we're supposed to be partners, but there's competing interests that sometimes come into play. One doesn't want to spend money, and one is okay with spending money. Because it's not their money, but you know they want to provide a great product for the public, and so the developer came and said, hey, you know, we agreed to this, but you know, we're not really sure if you're going to be able to see that. You know, we don't want to build something that no one's going to see. It's an architectural element. So you know, if you're coming on 121, you know, are you really going to see this rail in yellow? If you're coming out, are you really going to see it? We don't think so. There's a rail. So the project manager looks over at me and says, can you model that? And I said, gotcha. So that's what we did. This one's pretty ugly because this was like 2 weeks. But it gets the point across, and it kind of just shut down that private sector argument. So I modeled that rail specifically in green just to highlight it. So if you're driving on 121, you know, there's that direct connector that's going to connect downtown. You can see that rail in green. You can see it from far away. You can see it from close up. So here what was important was getting the vertical and horizontal geometry correct. This is an existing bridge, so I got their survey data. I went out and measured rail heights. I went out and measured, you know, that fence, took pictures. You'll see that there's kind of some bridge beams that are sticking up. Hopefully they don't construct it like that, but I just didn't, that wasn't important for this analysis, so I didn't change them. So they're coming out of downtown, you can see the green rail, and there's our little bridge beams. So this one was interesting. It had a shorter rail, different type of fence. So downtown connector, again, just integrating all those elements, the driving speed, seeing it 3D, seeing it from what a driver would see. And what this did is it allowed all these parties. You know, there's no arguing about will you see it, will you not. Hey, you see it. I just showed you in about 20 seconds that you're going to see it. So now y'all debate whether you want to do it or not. And so what that did was that saved us valuable meeting and debating time. And when you're spending $40 million a day and you get about $200,000 in toll revenue a day, you know, all that meeting time adds up. So conclusion, public-private partnerships are very conducive to producing very large, complex projects on a rapid schedule. These case studies just presented ways that visualization can help owners. They provide a fusion of complex information. They are very easily understood. You know, if you can see a video, you can see it. It helped them make timely decisions, and it's even more valuable for our owner, TxDOT, because of their strained resources and time. So, thank you very much. If there's any questions, then.
Questions?
I'm quit touching that.
Could you tell what software you use?
Absolutely. Autodesk, right, James?
You tell me.
Yeah, Autodesk is your friend. Autodesk is your buddy. So built them in Civil 3D and modified them to look pretty in just AutoCAD solids, and then 3ds Max for texturing, for lighting, and for camera generation. And then you can see my sweet video editing skills, right? Which is done in Microsoft Windows Media Maker. I want to get something fancier, but I don't have it. Someone else?
Other questions?
That was the same one.
Okay.
What's the source of the data, especially terrain and then all the three-dimensional data? How do you capture all of this?
So I beg and plead for the private developer to give me data, because they technically, or give me data that I can work with, not like PDF plans that I have to scan in and try to approximate. So I, for profiles, you know, used their plans. Some of this is schematic, so it's like this is the best, but I don't have to be. You know, I'm not building off this. This isn't being, you know, built off of. They're not, you know, taking elevations or anything from this. So I can have a little bit of flexibility. But I will tell you that, you know, I took their survey points for existing on bridges. I said, hey, I need this. You know, this is important. I have their horizontal geometry from DGN files. For terrain, in these areas, that wasn't super necessary. So, you know, like on the LBJ Express, the terrain was really just my roadway, so that was horizontal and vertical geometry. It's all from, so this is under construction right now. So most of the time I have plans, you know, to work with, and then, like I said, it's kind of interesting being on the public side, you know, trying to get the information from the private. So.
Was any of this, any of this georeferenced? And that is, any...
Yeah, no, that's, yeah, it's all Texas State Plain, so I get their DGN files, and then I have imagery from TxDOT, and then they have, it's always fun because everyone talks about georeferencing, but no one talks about the correction factor I don't know if it's unique to Texas or what, but it's like, you know, that's been probably one of the most fun challenges, is making sure that it all works well together. But so it's all, you know, I'm getting the real DGNs that they are using in the plane production. So, anyone else?
Any other questions?
So the speeds of the cars and the traffic operations piece in the animation, was it?
Traffic was fake. I just made it up. But
the analysis of the speed that you showed, like at this speed you'll see this, or for the merge, that kind of stuff, was that in what software do you use to bring that piece in?
in 3ds Max, you can take 3D lines and add a camera to it, and then set up kind of. I did some research to kind of see, you know, what does the human eye see, you know, field of view and blur distance, and so it was animating a camera.
Anyone else?
All right, thank you all.
All right, last but not least, we've got Alexander Badaoui.
Badaoui, close.
Badaoui with the
Yeah, if you switch it, that'd be great.
Gonna assist
HDMI.
with that as well. So, good questions for last. We've got about session ends at 3, so you've got 25 minutes.
Oh,
Maybe 10 more questions if you can. But yeah.
That's all right.
The two is on something. Yeah. You button?
Yeah, it should be plugged in. Something happened. There we go. Excellent. Okay. Rock and roll. All right. All right. Thank you everyone for coming. There's the microphone. Okay. So my presentation will be about developing the actual model that goes into what everybody's been talking about. So most of these talks have been about the final product that's been made. This is how to actually the engineering behind the model that's been made. So the technique that we're going to be discussing is called the 3D linear method. I pioneered to put templates across a road in the most effective and efficient way to save the most amount of time on a project, which everyone knows that time becomes money. So a little bit about myself. As you can tell from my voice, I'm actually from Australia. I moved here in 2014, but my experience does span across 4 different countries, and I've worked on many different large-scale infrastructure projects similar to the jobs that Cameron presented, and everything from desalination plants to power stations to multi-level viaducts. A little bit about the company I'm from, Terra Engineering. We are starting to develop our footprint in doing 3-dimensional design, and we've actually begun to train other firms in these techniques to be able to build their models in the most effective and efficient way. And we're also even trying to train the Illinois Tollway themselves and actually in their ability to analyze the models we give them. We also understand how these investments come into play to increase the efficiency and effectiveness. Those 2 words are going to come into play throughout this presentation. So why do we develop visualized models in the first place? And the primary purpose is to convey the intention to the community and the client. What you see on the left is a rendered model of a project that I worked on in Adelaide, South Australia, called the Urban Superway. And the picture on the right is the actual photograph of the same junction. So the advantage of that rendered model before it was built is the client being the Department of Transport and also the community was able to see what was there before it was built. However, that is not the primary purpose of why we build models. So why do we build models? The primary purpose is to make a centralized data source for all the information. This way, plan production, quantities, option development, eventually automatic grading machines, and visualization is a subcomponent to that. But this way, all the data can come from one source, and you're always guaranteed to get the result to be clean every single time, not the product of the visualization result. So the engineering application is really the true primary purpose of why you build these 3D models. These investments in 3D lead to much more increased efficiencies and effectiveness because we're able to make these products in one piece, and then the outputs come from that model rather than traditional way of building the outputs and then making the model from that. We have one centralized model, one place to make the changes, as people who know Lord of the Rings, one ring to rule them all, one model to control everything is the idea behind the purpose of building a centralized model. So, how are these models developed? This is what the current teachings will demonstrate. If you open up any package of a Bentley product or an Autodesk product out of the box, is to build one corridor per alignment. There are pros and cons to this approach. The pros being you get one corridor per alignment to get a simpler representation of the road. However, the cons, that's just a small part of the cons, but the biggest part I want to mention is the stuff in red. The road changes so often along the road that the templates you need to build are so complicated that only the person who made them can edit them and change them, because design builds, especially large projects, they change every 10 minutes about what they feel like on the road. So in order to be able to change the products, these templates need to be so comprehensive to cater for every scenario, it's too complicated. And if that person is hit by a bus, that person's sick, that person leaves the company, who's going to amend the template? And what I find is on some consultants, the person who built that template can't fix it 2 months later because they forgot how they built it. So is there a better way? Well, that's why we're here. 3D linear method is a clean way of building the same data, but with simpler templates. It's based on the exact opposite of what's the current out-of-the-box thinking of one template. Multiple corridors, you keep recycling the same template. For those who are familiar with the old school way of designing, criteria files may mean something or may not. What a criteria represents is a group of code of a simplified element, such as a curb, a pavement, a sidewalk, a parkway. I was about to say verge, but that's a very Australian term. Just bits and pieces of the road. That's the limit of the corridor, not further than just the simple cross-sectional element. Every single piece connects to every other piece, just like Lego. Each of those 2x4 blocks is a simple block, but if you get the blocks, you replicate the same blocks millions of times, eventually you get one overall model. Now that model, you can't put, if you put that into one template, you'll be still modeling it in 2100 because it's too complicated to make as one piece. But each of those pieces, a 2x4, a little 2x1 block, those pieces are easily created because of the simplicity of how they're made. So a little visualized demonstration are based on a Illinois tollway road. So 4 basic components of an Illinois tollway road, an aggregate shoulder, 3 components. An aggregate shoulder, we have this lane called Portland cement concrete pavement, I believe it's called. That's just the type of pavement that's used in the Illinois tollway, and an asphaltic shoulder. We have your typical section from an Illinois tollway job. Each of these pieces is a different corridor. Each of those circles is how they all connect. Because each of these pieces connect to each other, we now have a whole series of interchangeable pieces that we can change anytime we want, because sometimes you want to change a part of the road, not the whole thing. You cannot do that if it's one template. You can do it if it's multiple. I don't like that curb anymore. The client says, I want barrier. You just switch it out, reconnect. I want to put a lane in there. You insert it where you need it. And notice how the rest of the lanes have stayed consistent. So I've only changed parts of the template. Now we can go further and start to add external components to multiple roads. I want to add a ditch. I add it where I need it and connect it where it's required. I need a retaining wall and a parkway. I add it where I need it. I connect it where I need it. And I need safety. I need a piece of guardrail. Better put that in there. But I only add the pieces where I need them. And I connect them where I need them. And now, in between each one of those red lines represents an interchangeable corridor where the template can change anytime you want. So now you have an infinitely complex but yet simplified design because it's all made of lots of little simple pieces. How do we manage this mess? That is an understatement. I have a job which I'll be showing at the end, which exceeds 3,000 different corridors. How do you manage that kind of database? Well, centralized data with a very comprehensive yet concise naming convention. Now, the naming convention there is specified to the tollway. On the left column, they're the feature names and the point names and the level that comes out. There is more to the naming convention that comes with it, but the idea is to simplify the convention and make it compact so that way any software user can keep using that same convention over and over again. So how is this better than building a single template? Well, for example, for starters, the templates are simpler. The road designer and the engineer spends all the time doing what they're supposed to be doing, designing the road, not designing the complicated template. So they've got the library of templates and they can use those templates. A lane doesn't change. The section of tollway of PCCP and a subbase and a base course, that section has been around since the 50s. So that section it's not going to change anytime soon. You can use that template on any tollway project. A curb profile in the state of Illinois hasn't changed since the concept of curb existed because Illinois doesn't change very often. So that template, you build it once, you use it thousands and thousands of times on multiples of projects. So you spend the time creating the road, not the template that feeds into the road. The symbology. Now for Autodesk users, the layers that will come on. Layers and symbology and levels are all interchangeable terms. Because the templates are built consistently, the way they are visualized comes out exactly the same every time you use them, which means you can do digital quantity takeoffs en masse for an entire model if you use the same templates. It's very difficult to manage that if you build a unique template per scenario. You have to ensure the symbology matches for every point on that template. But with a simplified template, you always get a clean, reliable result every single time. You change only the parts that you need. Most of the time, the lanes are going to be the same, but what changes is the end conditions and the ditches. They're the ones that are variable. You put the effort into that, and for example, global change can now happen more effectively because you're using that same template a few hundred times. I said that pavement doesn't change. Well, sometimes it does. Sometimes this particular job will have a 12-inch pavement rather than a 10.5-inch. Sometimes the project needs deeper. You make a mass change on one template, every single corridor that's using that one template is now changed. You cannot do that in the other method of a single template. You have to go to each one and make the change. That is more difficult and more time consuming, and it can lead to a lot of mistakes, so you might forget about one. Be changed on the central source and they all get populated. And it is actually rather simple to teach. Surprisingly, connecting smaller blocks than making one big block, people get the principle rather quickly because they actually relate it to Lego. That's why I keep referring to Lego. It's that metaphor of the blocks connecting together. More people understand that better than one single template. So let's talk about efficiency of how generating this work. Complex templates, the single ones, do take longer times to process because the computer has to run through every single scenario, and the more components within that corridor, the more time it's going to process and the more computing resources it's going to take. Not everybody can afford 2,000 terabytes of RAM and a 400 gigabyte video card, but the complex templates require the heavy memory to make it run smooth and effective. With the simpler templates, the fewer scenarios you have to analyze, the less time it spends processing and less computing resources required. Now, I've had a lot of people say, well, okay, you got 3,000 corridors with simple templates. Is it quicker than one template? It actually is. The computing processing to run multiple thousands of corridors that are simple is effective by a magnitude of 10 compared to one template with lots of complex scenarios. That's how the program seems to work. So it does actually make it quicker to make lots of small parts than one big part. And the less processing time, the more efficient and the more money you save. Let's talk about accuracy. So accuracy is just as important as efficiency. Because everything's broken down to the smaller pieces, you put more detail where you need it. This particular diagram on screen shows the far on the left, that's the lane. The middle part is the gore, then there's a ramp, then there's another shoulder, then there's a curb, then an aggregate shoulder, then an end condition. Notice all those horizontal strokes represent different intervals of template drops. I don't need the detail on the main line because the main line is a very simple straight gradient, but I need more detail on the gore. So because each piece is its independent, unique corridor, I apply detail only where you need it, and you don't apply detail across the whole length. If you have a single template, you want detail on one part of the corridor, you need to apply detail on the entire width of the corridor. That increases your processing time and increases the chance of computer crashing, and therefore it adds the time to build the model, and it costs more money, and then you don't meet deliverables. But by having a smaller piece, you're able to apply the detail only where you need it. And the more detail you have, the more accuracy, which is pretty straightforward. So in summary of what this method represents, lots of pieces, simple design, everything joins together. The more efficient you have, the less processing time you have, and the accuracy is only applied where you need it on the job because it's broken up into the smaller pieces. While you're thinking of questions, this recent publication about the return of investment, the idea of the 3D linear method ties directly into this because it builds the model in a quick processing time. So I will demonstrate a model that has been developed. The model construction time, it's a little bit of an understatement because it was 3 operators with a couple of months, but that was also designing as well as creating the model. But if we knew the design from the start, about 40 hours because it's a multi-level interchange. So let's go into it and have a look while you're thinking of questions. So are there any questions while I'm bringing up my lovely little model? Where's my mouse? Oops. So this here is the 3,000 corridor beast. Multi-level interchanges, retaining walls, all the super is done, all the lane pavements are done, the barriers are done, all the end conditions are all correct because it's based on what the engineers wanted. The parts that aren't in there are utilities, because another program comes and superimposes on that, and the substructure of a bridge, because another program comes and superimposes on top of that. But all the civil elements are there. It's a concept phase, so we didn't bother modeling the rest of the guardrail, but we got most of this job. And you can see, you can zoom in, have a look. Each of these pieces is a unique corridor. So lots and little pieces joined together. And because everything's consistent, I can do level symbology. Just none. I want to see, that's all my topsoil. One hit quantity, all done, because it all comes from the centralized model. You can't quite do that if you have one piece of template, because you need to ensure that each piece is correct. But while I'm babbling, is there any questions, actually? Yep.
I guess common question together, mixed. So this is a great idea, right? Building a database and then using the data from the database to then visualize. I mean, that's what GIA has been doing for years, where the fundamental is the database and then the graphics sort of feeds from it. And then what you call Legos typically, I would probably call these section 3D primitive. I'm assuming every single of these element or primitives that you're building is 3D, right?
Yeah, they actually, this is what they are. This is an actual Bentley package, not an Autodesk package, but it's a very similar operation to Civil 3D. So let me go into, these are what the pieces are made of. So they are a sectional plane that just has a curb. So it's a cross-sectional element that gets projected along a prism using an alignment. So that's what it is. It's a 2D section that gets projected on the third dimension. Well, actually, this is a YX plane. Oh, sorry, a YZ plane, and then the X plane is along the.
Extruded.
Yeah, they're extruded planes. That's how the program seems to work.
How are these assembled together? Are these visually, manually done, or is there some scripting, like for example, or you can have some rule-based, so like create this array or follow all this primitive A follows path B, things like that?
Well, there are two ways you can connect templates together. So in this program, there's a thing called a point control. So each one of these templates, and we go to a lane one. So let's see, pavement, where is it? Pavement, main line. So each one of see these little red crosses? They represent different points. Every template has a ref point here and a width point there. I connect the ref point to a width point via the interface known as a point control, which is a drop down in the program. And that width point connects to another ref, which connects to another width, connect another ref. So then that's how they daisy chain together. The other way to control it is each one of these points can be controlled via a parametric constraint, which the program can read. So that width value, by default, it's going to be reported as 12 feet to the right because it's 12 positive. If I want to change it, I insert the template into the program, and then it comes up with an option known as a parametric constraint, which is here. It's probably not going to work for me because I don't have full access to the database, but the parametric constraint, then I click on the corridor and lists all the ways I can control that parametrically, then I switch the pavement over. Or the slope, I switch the slope over because I changed from what the default setting is. So that's how you can control that mechanism.
Other questions?
One thing I'm like,
You spend more time on rather than the building side. You spend more time on the connecting points.
pretty much. Yeah, I spend more time connecting the blocks together. That's where the effort comes in. And that's actually a lot quicker than building this ginormous, ugly template that takes a year to finish. Yep.
As far as applying texture to this, you get, like, take your process and wet it with Canva's output. Is there any sort of processing or any sort of step that needs to be interjected in that to get from this model to that realistic
This is
photo, you know. photo.
Cameron mentioned that he can take DGNs. This is just a DGN. So you can take that model and supply skins.
It'll probably export out as a mesh, and then you can texture a mesh.
Yeah, these things are all meshes. So it can export out and then you can make it pretty.
Yeah.
I mean, from an engineering point of view, I prefer the solid colors because I understand that yellow is PCCP pavement, but the average builder would go, what the hell is yellow pavement? My road's not yellow. It's grey, so that's where the texture would come into play.
That's the disconnect for the public. They're like, everything's gray.
Yeah, and structure, and for some reason in Illinois, all structural elements have been rendered as pink. It's just a historic color. That's just what they do. So that's why all the bridges are pink. There's no engineering reason why it's like that. It's just a historic reason. And aggregate shoulder is red. But I don't know why it's red. It's just red. But there's strange reason. And topsoil is blue for some reason. But yeah, it's very historic reasons for colors. But this is an engineering output. That is a pre-information that will go into what Cameron's model does. This is like the behind the scenes.
Any other questions?
I was just gonna ask, I guess, have you done any quantification of the time saving and all those criteria you established to compare the traditional template-based model with this pyramid or 3D linear that you call it?
Not a formalized study, but proof of concept by the fact that we managed to save a few $1 million in budget, because the budget originally was catered for 50,000 hours of creating cross sections. I was able to create it within a day because it's from the program. So there are and then those hours became modeling hours. So there's realistic time savings based on if the initial job is budgeted to do methods in the traditional way, and then you do it via this way, then you'll see the result on the fact that you've saved budget and hours. But no, I wouldn't say a formal university study has proven that two projects parallel, one will be doing things the old-fashioned way and one doing things the new way. It's usually intuitive by the time the outputs come out that yes, you have saved time, and time is the money factor.
Thank you guys very